Okay, so I'm going to talk you through a couple of circular motion questions today that have caused people some problems. And we're going to start off with question 4. This question 4 said, what is the period in seconds of a satellite that completes 7 complete orbits of the Sun every 24 hours? So if it's completing a full orbit in 24 hours, then its period is going to be 1/7 of 24 hours. So that's the amount of time it takes to complete an orbit. So let's just try and get that because it asked for it in seconds. And we'll calculate it out first of all as a decimal, and then we'll get it in seconds. So for me, the most intuitive way to convert from hours down to seconds is to first of all convert it to minutes and then to seconds. So to convert from hours to minutes, we multiply by 60 because there's 60 minutes in an hour. This gives us an answer of 205.74 minutes. So now we've gone from hours down to minutes. To get to seconds, we're going to do the same thing, multiply by 60 again. And that gives us 12,344.4 seconds. So for part B of question 4, they ask us to find the radius of its motion. Now we already have the period, so we're going to try and use the formula that relates period to radius. And that formula will look like this. So we know what the period is, we know what pi is, we know universal gravitational constant, and we're given the mass of the planet as well. So we'll be able to solve for or then because we know all the other variables there. So let's start filling in what we do know. So when we fill all of that in, it will look something like this. For the gravitational constant, I'm using 1 decimal place, and for the mass of the Earth, just one significant figure also. Not because that's the best way to do things, but it's because the way they do it in the book. So in an exam, I'd use 3 decimal places as standard, or whatever amount they give you in the question. It's even more preferable. Just trying to get the answer here to look pretty similar to what it is in the book. So when we try and simplify this a little bit, our period squared on the left side gives us 1.524 by 10 to the 8, and the bottom of the fraction on the right hand side gives us 4.02 by 10 to the power 14. Now for the sake of keeping or cubed as its own entity over here, I'm just taking it outside of that fraction, so that means that we can simplify this whole fraction here in a way that we kind of get rid of or cubed or having to deal with it. We can just multiply it by or cubed afterwards. So our fraction on the right then will simplify to 9.821 by 10 to the power of minus 14. And that still needs to be multiplied by or cubed. And on the left hand side, it'll stay the same. So to try and get towards solving this now, we can say that or cubed is equal to 1.524 times 10 to the power of 8 divided by 9.821 times 10 to the power of minus 14. When we try and simplify this fraction on the right hand side, we'll get 1.552 times 10 to the power of 21. And then just to solve for or at the end, we're going to get the cubed root of both sides. And our cubed root here will work out as 1.158 by 10 to the power 7. Now our unit for this, because it's radius, is going to be meters. Now in the back of the book, if you check your answer off against that, it gives the answer in kilometers, which is fine. So we're on to question 6 now. Question 6 talks about the International Space Station, which is in orbit at a height of 400 kilometers above the Earth's surface. They want us to find the period of the space station's motion. So what they're doing here is asking us to use this formula again, because they're giving us radius and they want us to find a period. So the exact same formula, it's just that this time we're trying to find t instead of trying to find r. Now there is a small trick here. They're telling us that the satellite is in orbit 400 meters above the Earth's surface. Now I think that the trick is they want us to say that the radius is 400,000 meters, which I think a lot of people might be tricked into doing. But you need to remember, if this is our Earth here and the satellite is here, if this is 400 meters above the Earth's crust, that doesn't mean that it's the radius, because we still need to account for the Earth's radius and add that on. 400 kilometers here. So if you look at the radius of the Earth that we were given in the sample questions, it says the radius of the Earth is 6.4 by 10 to the power of 6 meters. So just to recap then, this is our 6.4 by 10 to the power of 8. And we're going to add, 10 to the power of 6. And we're just going to add that to the 400,000 meters that the satellite is away from the Earth. So if we do that, we'll get out our answer for the radius. That will give us 6.8 by 10 to the power of 6 meters. Now we can fill that back into our original formula. T squared is equal to 4 pi squared. We now know the radius is 6.8 by 10 to the 6. That's going to be cubed, and then divided by 6.7 by 10 to the power of minus 11, a universal gravitational constant. Again, if I was doing this in an exam, I'd use more decimal places. I'd use 3. But I just want to use the method that they use in the book, because it'll give us the closest answer to the book's one. And then the mass of the Earth is 6 by 10 to the power of 24 kilograms. So we can actually solve this right inside out now. I advise doing this top half first, really going step by step. It's the kind of thing that if you put into calculator, it's very easy to make mistakes with. I actually tried banging the whole thing into my calculator just now, and it gave me the wrong answer. So I did it piece by piece then instead, doing this part cubed first, then multiplying it the whole top row, whole bottom row, and then finally dividing. But the final answer I got was 3.072 times 10 to the power of 7. That's still t squared. So to get t, we want to get the square root of this. And the answer that we'll get is 5.542 by 10 to the power of 3 seconds. Or if you want to write that out in a non-scientific notation form, that would be 5,542 seconds. Now, for our final part of question 6, we're asked to figure out how many times that satellite would orbit around the world in 24 hours. So we're going to get 24 hours and divide it by the amount of time it takes for the satellite to orbit, which is going to be 5,542 seconds. So dividing the 24-hour period into a bunch of different chunks, each with the period as its length. Now, obviously we can't do this straight away. We want to convert the hours into seconds first of all, so the units are the same. You could go the other way around, but let's just convert it into seconds because that's the standard international unit. So we'll use the same method as we did before. We'll convert it first of all into minutes, which will give us 1440 minutes. Then we'll multiply this by 60 again to get it in seconds, which will give us 86,400 seconds in a day, or in 24 hours. So now we'll go back to what we're originally at. We want to divide 24 hours by 5,542 seconds to see how many times that period goes into a day. So we'll write this out in seconds. 86,400 divided by 5,542 seconds. Again, now they're both in seconds, so it'll make more sense to divide them that way. This will give you a final answer of 15.59 times that it's going to go around the Earth in 24 hours. Now it might seem weird that we don't have a unit here, but they're just asking us how many times does it go around the Earth. And if you look at the unit analysis, we've divided seconds by seconds, so they'll actually both cancel out. So our answer will just be a number.